So now at long last, after we've talked about the server, we've talked about the client, it's time to talk about the driver implementation. We're going to talk about how we wrote a program to test how this whole thing works and how it performs, which is kind of fun. So that's, of course, on the client side. And the code we're going to look at, as always, is in the EX1 project in my web MVC folder in my live lessons GitHub repository. So here we are back in my GitHub repository. This is the driver. You can see it's nestled under the test directory inside of the source folder in the EX1 module. And a couple things to note here. This particular test is a Spring Boot test. So Spring Boot tests have certain cool properties. We also use those for your assignments that you've done up to this point. And basically what they allow us to do is they allow us to be able to pick one microservice and then write a test where this test program and the test apparatus that's provided by Spring Boot will automatically launch the microservice and then allow us to test it. There's some limitations with this I've not been able to figure out yet. Perhaps my knowledge is limited, but the way I see it is you use testing to test one microservice at a time. If you want to test more than one microservice at a time, from what I can tell, you have to do other stuff that is not quite as plug and play as this is. So you can see here we auto-wire a few things. We're going to auto-wire the client for the parallel streams. We're going to auto-wire the client for completable futures. We're going to auto-wire the client for structured concurrency. And then we kind of set some parameters here because we don't really have a command line since this is actually running as a test. So @test is an annotation that says run this as part of the test framework. So when we run this thing, this particular method will get called. And I'm just going to start that running because it takes a little while to start up. So here's what we do. We go ahead. First, we're going to generate a bunch of random numbers up to a certain amount, up to a certain value. You've seen this a million times before. We generate count random numbers within a range. We box them so we have a stream of integer reference objects, and we convert that into a list of integer objects. And then we're going to go ahead and time 3 tests, or actually more than 3 tests. So we're going to take each of the different concurrency strategies, completable futures, parallel streams, and structured concurrency, and we're going to test them both with parallelism on and off. So I think we have a total of 6 calls. So we test individual calls for parallel streams without parallelism, with parallelism, and so you can see we just kind of go through and try all the different combinations. And I guess we actually test things with both parallel individual calls on and off and parallel list calls on and off. So we end up with a whole bunch of different permutations. Here's the test program. The test program prints off what we're doing. It is given a by function, which is the test to run, the list of prime candidates, whether we want to run in parallel or not, and the name of the test. And then it goes ahead and uses that run timer method we've talked about many times before in order to be able to apply the test, record how long it took to run, and then stash that away so we can print it out when we're done. And of course, we always garbage collect first so that we don't have issues with memory garbage collection perturbing the results. So when we run all these tests, we get a bunch of results, and here's what they look like. So you can see here, this particular case has 500 integers that we're checking for primality. And here are the results. So you can see that structured concurrency, completable futures, and parallel streams all execute very quickly. You'll also notice, interestingly enough, that the completable futures version that was sequential also executes fast. I think it's because my implementation is incorrect. But ignore that one for right now. We'll come back and look at that later. I think it's always doing things in parallel. So of course it's going to be fast, so it's going to perform just as well as the parallel version does. But the thing to note is that these guys all take about the same amount of time to run. And you should also notice that the case where we do the concurrency on the server side is faster. And that's because we're passing the list over once, and then all the threading's taking place on the back end. So there's only one communication of the original list of things and then getting the results back. In contrast, when we do the individual calls in parallel, they do run faster than the sequential calls. The sequential calls are always slower. However, notice the individual calls are slower than the individual calls. Remember, the individual calls, to your earlier question, are doing concurrency on the client. And so we still have concurrency, so that's a win, but each of those calls has to go across from the client process to the server process. Now, keep in mind, this is running on my local machine, so that's not a very far distance, but it does have to transition across from one process through the OS kernel to the other process. And that takes time. So there's overhead associated with each of those calls. So even though we're running them in parallel, there's more overhead to do lots of small calls from the client to the server as opposed to sending over a big chunk of stuff and having the server crank away on it in parallel. So the basic point there is there's overhead from these round trips. And some good analogies here just to give you something to think about. If you ever go to an airport and you want, let's say there's a big conference and a whole bunch of people show up to go to a conference and they're going to go to the conference hotel. There's sort of two ways to get there. Each person could get into an individual taxi or Uber or Lyft one at a time and be driven there and back. That's one way to do it. And there might be a line of taxi cabs, right? Or you could have a shuttle bus and the bus fills up with people and then the bus drives them all and drops them off. So the model with a lot of parallel individual calls is kind of like each person taking their own cab or their own Uber or Lyft. And the other model is where they all get into this, they all file into this bus and go in one fell swoop. So there's a few trade-offs, right? If you're lucky and you end up being the first person in line at the taxi stand, you may get there faster. But chances are, especially if there's only a limited number of taxis, it's going to take a lot more time and certainly probably burn more carbon to do it each individual one with each individual cab. Whereas where you fill everybody up in a bus, it may take you as an individual longer, but the whole collective will probably show up faster. Now, of course, there's another issue with that, which comes down to other sources of overhead in a system. So if 200 people show up in a bus at a hotel, it's going to take forever for those people to be processed, assuming you don't have like 200 clerks. Whereas if they show up in dribs and drabs in their taxis, you can basically smooth things out. So each person might experience less delay. So the point is that thinking about optimization has to be thought at a system level. But at any rate, for this particular example, you can see that putting things over in one fell swoop and running in parallel is faster than doing things one at a time in parallel. But all of those things are faster than doing stuff sequentially. And so what you find is that the list sequential calls are faster than the individual calls sequential, but they're slower than the parallel calls. Which is pretty much, I think, what our intuition would be if we studied if we worshiped the altar of concurrency long enough. We would understand that that would be what we would expect. But it's just kind of fun to see it demonstrated in an actual performance test to illustrate the pros and cons of the different approaches.